Hello, everyone. At the outset, let me express my heartfelt thanks to Dr. Murlidhar Kanchi and the organizing team for inviting me in this prestigious annual echocardiography meeting. My topic for discussion today is physics of cardiac ultrasound and image optimization by learning knobology. It is difficult to have a comprehensive discussion on my topic today within the time frame of the lecture. So I'll try to highlight only the key learning points. Also, this topic in relation to 3D echocardiography and speckle tracking will not be discussed for the same reason. Now, sound is transmitted as pressure waves, causing alternate rarefaction and compression, as you can see in this photo, through the medium it travels. Ultrasound is defined as sound with frequencies above 20,000 Hertz. However, diagnostic medical ultrasound uses much higher frequencies in the range of 1 to 20 megahertz. The transmitted wavelength is important. Shorter the wavelength, higher is the image resolution and sharper the image. However, the wave can travel shorter distances and thus fail to penetrate deeper structures. Take home message: select the appropriate probe frequency to ensure adequate penetration to the tissue of interest while ensuring optimal image quality. Piezoelectric elements in the probe transducer emit ultrasonic waves that are partially reflected back from layers of different tissue densities. These received vibrations are then transformed back into electrical pulses, which are converted by the scanner into a digital image that we see on the screen. When ultrasound wave interacts with tissues, bits of it are scattered, attenuated, or refracted. But the basis of ultrasound imaging is reflection. How much of ultrasound will get reflected depends on the acoustic impedance between tissues. Optimal reflection, hence optimal image quality, is achieved if the direction of the ultrasound beam is perpendicular to the object bounded. We will now discuss a bit about knobology. As you can see, there are several functions on the control panel. Hence, we will concentrate only on the applications that echocardiographers routinely use in their daily practice. The first such application is two-dimensional echocardiography, also called B or brightness mode. Using this knob directs each reflected sound wave to be displayed on screen as a point. Brightness of these points depends on the received energy using a grayscale. The sector scanner in brightness mode electronically sweeps across a plane, creating a cross-sectional image of the field of interest. M mode. Here, only one scan line is utilized and the signal is recorded in brightness mode against time. What is the use? M mode is ideal for imaging of rapid cardiac function. Now, the fundamental important thing is to get a good image by using knobology. And this is something called the image optimization. A few take-home messages that I want to stress on is use the smallest field of view. The field of view is usually the plane or the area of interest that we are scanning. The smaller we use it, better is the picture. Zoom is a post-processing function that simply enlarges the pixels without improving fundamental resolution. This is a post-processing function. There are in certain machines a pre-processing zoom available also. Power is important. It is the rate of energy delivered in the transmitted sound wave. It is important to adjust the power to the highest level to within the thermal limits to avoid the probe overheating and damaging internal tissues. Depth is very important because the more we increase the depth of interrogation, the pulse repetition frequency gets reduced and hence the resolution becomes worse. The sector width is also important because we need to keep it at optimal. Unnecessary large sector width will cause a higher pulse repetition frequency, a lesser pulse repetition frequency and a poor image quality. So sector width has to be kept to optimum. Gain has to be minimized for optimal image quality. As a rule of thumb, fluid and blood should be black, myocardium should be medium gray, and pericardium and all calcification should be bright white on the gray scale. Time gain controls, they are used to regulate gain at a given distance from the transducer vertically. The lateral grains regulate the gain along the set of neighboring scan lines horizontally. Brightness, contrast, colorization, grayscale, these are all post-processing controls to enhance image. So this is an example. Here in the mid-esophageal four-chamber view, the measurements using all the buttons whose functions we just described are displayed on the left-hand side of the screen in the yellow box. Namely, what kind of probe is being used, a frame rate of 36 Hz, a depth of interest at 12 centimeters, and a 2D overall gain at 50. This slide shows the very important applicability of 2D gain. In the mid-esophageal aortic valve short axis view, when the gain is set at 20, the three aortic valve leaflets are not visualized on the left-hand image, on the left-hand side image. Now, once we have increased the gain to 50, you can, on the right-hand side of the image, see that all the three leaflets are nicely visualized. This is a transgastric mid-papillary short axis view. In the left-hand frame, the septal wall is poorly defined. Here we are using a lateral gain control. And now after applying that, on the right-hand side, you can see that both walls are now adequately visualized. In this mid-esophageal four-chamber view, the time gain has been used at the level of the lateral tricuspid annulus. On the left-hand side, it is hardly being seen. On appropriate use of the time gain control, you can see a high gain at the level of the lateral tricuspid annulus. Coming to Doppler echocardiography controls, it is not possible to explain the Doppler principle and the Doppler equation, which calculates the Doppler frequency shift. However, two things are important for practice and need to be remembered. One, the angle between the ultrasound beam and the axis of the blood flow shouldn't be more than 20 degrees and ideally parallel to avoid erroneous calculation of blood flow velocities. And two, angle correction, which is frequently used in vascular Doppler, should never be used in cardiac ultrasound. Now, in Doppler echocardiography, there are principally two modes. In continuous wave Doppler echocardiography, the transducer uses two crystals. One crystal is used to continuously emit the ultrasound signal, and the other crystal to continuously receive the reflected signal. The advantage is we can measure very high blood velocities in excess of 7 meters per second. On the flip side, the origin of the signal can't be precisely located. This is called range ambiguity. In the other Doppler modality called pulse wave Doppler, a single crystal is used to both transmit ultrasound wave and receive the reflected wave. Here, there is no range ambiguity, but the maximum blood velocity that can be measured is limited by the time needed by the sound wave to travel to the depth of interest and return to the receiver, which is known as the pulse repetition frequency. This brings us to the phenomena of aliasing, which happens in pulsed wave Doppler mode when the velocity of blood at the area of interrogation is beyond a particular limit known as the Nyquist limit. The Nyquist velocity limit is equal to half of the pulse repetition frequency. If aliasing happens, the direction of blood flow is depicted as opposite to that of the actual one, and the upper end of the velocity spectral tracing is cut off and displayed at the bottom of the scale. Potential remedies to this important aliasing artifact are lowering the baseline and increasing the pulse repetition frequency by using the smallest possible field of view. Now, in the color flow Doppler modality, the measured velocity and direction of blood flow is superimposed to a color pattern, where red indicates blood flow towards the transducer and blue away from the transducer. Velocities are assigned different colors on the color scale, with laminar flow depicted as homogeneous color and yellow and green representing turbulent blood flow with higher velocities. Finally, we come to tissue Doppler. Here, velocity of the myocardial tissue is measured as opposed to velocity of blood cells. Tissue Doppler is routinely used to assess left ventricular systolic and diastolic function, as also right ventricular function. Thank you so much for the opportunity to present in this important echocardiography meeting.